Okay, this is nuclear reactions. When you're talking about nuclear reactions, we like to mention that you've got two forces within the nucleus. Okay, nuclear reactions. These are reactions happening within the nucleus of an atom. Okay, so you have electrostatic force. Okay, an electrostatic force is going to try to pull the nucleus apart. Okay. Try to pull the nucleus apart. And the second one is a nuclear force. And nuclear force basically holds the nucleus together. Okay. And the bigger the element, the more electrostatic force you have. So the more unstable they are, the more quickly they break down. All right, and with the smaller ones, they don't have as much electrostatic force, so the nuclear force is much stronger and it holds it together very well. So keeping those two things in mind, we're going to talk about fusion and fission. Okay, first one is fusion. Okay, if you fuse something together, you're going to take two things and you're going to make them one. Okay, so this is two small nuclei becoming one large nucleus. Okay, two small nuclei becoming one large nucleus. Okay, and what you're going to do is you're going to have a little bit of energy. All right, you're going to take that energy and put it into two small nuclei. All right, and label that nuclei. Okay, and what you end up with is one large nucleus plus a large amount of energy. Okay, large amount of energy. Okay, this is used in hydrogen bombs, and it actually happens in stars. Okay, so if you remember your space unit from freshman year, fusion is what gives stars their energy and gives off all that light. Okay, fission is the exact opposite. Fission, we're taking one large nucleus and splitting it up. Okay, so we're going to take one large nucleus, okay, split into two smaller nuclei. Okay, and what we do here is we have a little bit of energy. Okay, we're going to energize that nucleus a little bit. We're going to throw a neutron at it. Okay, shoot it with a neutron essentially, plus this large nucleus. Okay, and what you end up with is two smaller nuclei plus large amounts of energy plus more neutrons. Okay, and then those two neutrons go off and hit two more large nuclei, and those break apart into four and shoot out more neutrons, and it's that chain reaction. It's how the atomic bomb works. Okay, so these are atomic bombs. That it works on that concept of a chain reaction. Okay, all right, and it also takes place in nuclear power plants, which is why a lot of people are nervous about nuclear power plants, because of the atomic bomb. Okay, and that's just the difference. You really just need to know the difference between fission and fusion I'm not going to ask you about, I'm not going to ask you to draw this or anything. I just want you to know that fusion is putting two things together and fission is taking things apart, and maybe a couple of examples. Okay, so if we were to move on to radioactive decay. And radioactive decay is basically breaking down the nucleus. Okay, and you have three different types that we're going to talk about. Okay, alpha, beta, and gamma. So the first one we're going to talk about is alpha. All right, alpha. In an alpha decay, you have two protons. All right, you got two protons and two neutrons. Neutrons. Okay, this is positive. Okay, because all it is the two protons and the two neutrons, so there's nothing negative to counteract those positive charges. Okay, and this is also, you can stop alpha particle radiation with paper. Okay, so if you were to take a big poster board and stand behind it, I could shoot all the alpha radiation I wanted at you, and you would not get contaminated with it. Okay. If you were to write an alpha particle just in an equation, you've got your alpha symbol, all right, and then your mass number, 4, because 2, okay, 2 here, and 2 neutrons, add those together, you get 4, and then essentially the atomic number from the 2 protons is 2, so that's going to be your alpha particle that you're drawing, okay, or you could draw it like helium, because essentially it is helium. That's what it is. It's got 2 protons and 2 neutrons. It just doesn't have the electrons. Okay. When something is put through alpha radiation or alpha decay, and we'll look at a couple of examples here in a second. Okay. When something is put through alpha decay, you're going to decrease the atomic number by 2. And the atomic mass by 4. Okay, so it decreases atomic mass by 4. Okay, or sorry, not atomic mass, mass number, same thing. Mass number. Okay, so let's look at an example. And if you remember back to the law of conservation of mass or matter, you want the same numbers on the left as you do on the right. So if we're looking at osmium 188, that's our isotope. That's our radioactive isotope. So we're going to draw the symbol, okay, of osmium 188. So that's OS. Mass number is at the top, 188. You're going to look at the periodic table, and you're going to see that osmium has an atomic number of 76. So that is our symbol for osmium 188. All right, and then it is going to undergo radioactive decay, alpha decay, so it's going to break apart into an alpha particle. So you're going to draw your alpha particle, okay? And then you're basically going to subtract 188, okay? 188 minus 4 is 184. 76 minus 2 is 74. Okay, then you're going to look on your periodic table. What element is number 74? Okay, and that is tungsten, W. All right, so what you have here is essentially a math equation. Everything on the right side has to add up to everything on the left side. So your atomic numbers are 2 plus 74, okay, and that's 76, equals 76. And over here, 4 and 184, added up together, gives you 188, all right? So you need to make sure that they add up. If they don't add up, you're doing something wrong. Do another example. Uranium 239. All right, look on the periodic table. Uranium is a U. It's number 92. Go through alpha particle decay. Okay, you need to be able to identify both the HE symbolism and the alpha particle symbolism. Okay, 4 over 2. It doesn't really matter which one you draw on a quiz. And then you're going to subtract from there, okay? 239 minus 4, 239 minus 4 gives you 235, okay? 92 minus 2 gives you 90. Look on the periodic table. Number 90 is thorium, TH. And that's alpha particle decay. That's alpha decay. Okay, let's go over beta decay, beta particles. Okay, beta particles are a little bit stronger. Okay, a little bit too low. All right, beta particles are a little bit stronger. They are symbolized with a beta symbol, which looks like a B with an extended stem on the left, and a 0 on top and a -1. Okay, or it can be drawn like that. Essentially, it's an electron that's being shot out there. All right. So, basically, what is happening is a neutron is being split into a positive and a negative particle, and that negative particle is moving on somewhere. Okay, so these are negative in nature, right? And beta particles can be stopped with wood or aluminum. And if you wrapped yourself in aluminum foil, I could shoot you with as much beta particle radiation as I wanted to, and you wouldn't get hurt. Now, if you were to stand there with a piece of paper like you did with alpha, the beta particles would go through that paper. So the paper is not going to be a good protective equipment for beta particle radiation. Okay. With this, your mass number goes up, mass number does not change. Okay, and your atomic number goes up by 1. All right, so let's look at a couple of examples here. Okay, a couple of examples. You've got potassium 42. All right, so you're going to draw your symbol. Potassium is K. 42 is your mass number. It's going to go on the top. Your atomic number for potassium, according to the periodic table, is 19. So there's our symbol for potassium 42. Okay, now it's going to undergo beta decay. So you're going to draw your beta particle. Okay, and essentially it's the same math. Okay, you're still gonna subtract left to right, but because this is a negative, it kind of throws a wrench into it a little bit if you don't remember how to subtract negatives. So 42 minus 0, okay, is still 42. Now 19 minus a -1, essentially 19 plus 1, right? So 19 plus 1 is going to give you 20. You're going to look on the periodic table and determine what element is number 20. That is calcium. Okay, and so you write the symbol for calcium. So when potassium 42 goes through beta decay, it becomes calcium 42. Okay, let's do one more example, and then we'll get into gamma radiation. So we're going to go to antimony 129. We're going to look at the periodic table. Let's erase this. 129, you're going to look at the periodic table and look up what the symbol is for antimony, and it's SB, and its number is 51. Okay, so there's our symbol. It's going to go through beta decay. So again, you need to know both of these symbols, okay, for a quiz or a test or something like that. Going to go through beta decay. 129 minus 0 is going to give us 129 again. 51 minus a -1 is essentially 51 plus 1 is going to give us 52. Look at your periodic table. Number 52 is tellurium, Te. Okay, that's beta decay. Let's go over gamma radiation. Okay, gamma radiation. This usually accompanies another type. Okay, rarely will you see just straight up gamma radiation or gamma decay. Okay, this is massless and high energy. Okay, it destroys living cells, tissues. Okay, and also, if you're a comic book fan, it created the Incredible Hulk. Okay, if you've seen any of the Avenger movies or any of those type of movies. Okay, so gamma radiation, it's either going to kill you or it's going to make you into a big green angry monster. Okay, that's pretty much it. This is blocked by lead. Okay, so if somebody was shooting gamma radiation at you, you better get behind some sort of lead block. All right. The symbol is basically looks like a fish that's taking a nosedive, with zeros on both the top and the bottom because it has no mass, so it has no atomic number, it has no mass number. Okay? No charge on this either. Okay? No charge. So if something were to, because it has to go through some other type of radiation along with gamma, let's just go over one that's going through alpha radiation. So if we had gallium 73, okay, and we want to put that through alpha and gamma radiation, okay, go through both of those, you're going to draw your alpha particle and your gamma particle, right? And then you're going to do the same kind of math. 73 minus 4 minus 0, okay, gives you 69. And 31 minus 2 minus 0 gives you 29. So look on your periodic table, number 29 is copper, okay? You could also do the same thing with beta and gamma, and then you just put essentially the initial particle through beta radiation and then through gamma as well. The math is going to come out the same. Okay, now let's look at this. If we were to have a little box that shot out radiation, okay, and we were to put it through a little chamber that is positive on one side and negative on the other side, okay, and let's say that we went alpha radiation first. So alpha radiation is positive. So through the chamber, it would start to bend upward, okay? That's alpha because it's positive. It's going to be attracted to the negative side of the plate, okay? The beta radiation, let's say we shot some beta radiation. Let's do it in a different color. Beta radiation in blue, eventually it would start sinking towards the positive plate because beta is negative, okay? And then if we shot gamma radiation, because it has no charge, no mass, it's going to go right through the middle because it's neutral, okay? This is important. You need to know how these things react when put into a magnetic field, okay? That is nuclear reactions.